Hello, it's 2025 in summer, and this is a revision seminar for dynamics, the first and probably last ever revision seminar for dynamics at the University of Adelaide. We'll see what happens at Adelaide Uni. We've got some faithful souls here, about 10% of the course cohort, who have given me some requests, and we're going to give it a go, and have helpfully sent me notes and things. So thank you to them. And we'll give it a go. So I've been asked to talk about chain rule and time derivatives and accelerations and stuff with respect to time and position and integrating and that stuff, which is near the beginning of the course. Says to me I should so come into the class, says at the beginning of semester 2, to help deal with those at the time when you're learning them for the first time. But it'll be too late for you guys, but we can deal with it now. This is the 2021 exam. And it has, just going to check if it's the one that I was looking at before. Yeah. And it's got some questions of that flavor, so I thought we'd give that a go. As our way of trying to talk about that stuff. So let's see. I'm going to read it. Ball passing through air experiences an aerodynamic drag force that produces an acceleration of A is minus B V squared, where B is 0.04 meters. 0.04 per meter, meters to minus 1. If A is in units of meters per second squared and V is a velocity in meters per second. Okay. If the initial velocity of the ball is, and they've given me a number, which of the following is closest to the velocity after 6 seconds has elapsed? Right, there's a lot of information there, and there's one formula and three numbers. Well, not including the number that's in the answer. Okay. So I'm just going to write some of that stuff down. So we have a ball, and there's air, and it's going at whatever speed it's going. And the acceleration is minus BV squared. B is 0.04. That makes sense for it to be meters to the minus 1, because this is in meters per second and all of that squared. So that's meters squared per second squared. And so if you divide by one of the meters, you'll get meters per second squared. Okay. That freaked me out for a bit. Okay. And V naught is 12 meters per second. And we want V at time being 6 seconds. Okay. All right. So that's the original question. And I'm thinking that to process this, I'm thinking that when time is 0, V is 12, and the acceleration is minus 0.04 times 12 squared, I guess. Yep. Okay. And when t is 6 seconds, the v that's the goal. Yep. And the acceleration will be still minus bv squared, but we don't know what that is yet. Okay. Okay. Sometimes it helps me to just write down the 2 moments that I've been asked about, so that I can think about them. So the thing I noticed the most here is that I've been asked what the velocity is at a specific time, but my formula that involves velocity does not involve time directly. And so this was exactly the sort of thing that you were talking about, where you're going, okay, well, how do I get time out of these formulas when it's not mentioned explicitly? Okay. Well, the first thing that occurs to me is to think about how the relationship between acceleration and velocity usually. So this is currently a relationship with acceleration velocity, and the relationship between acceleration and velocity is that the acceleration at any moment should be the derivative of the velocity with respect to time. Okay. Sweet. And that does have velocity and time in it. And my question tells me, is actually asking about the relationship between velocity and time, because it's saying what's the velocity at this specific time. And so this has velocity and time, so that's what I want. So I am now going to say that dv on dt is minus bv squared. And now I have an equation that involves both velocity and time. It's a differential equation, but that's good enough. And so now we are going to come to the part that physicists feel a lot more comfortable with than mathematicians, but mathematicians are okay with it. We're allowed to split apart our d things in derivatives. And so what we're saying is that very small changes in velocity are related to very small changes in time in this way. And traditionally, when you solve differential equations of this type, you need to get all of the same variables together. So I'm going to move the v over here. And it's really important when you do differential equations like this, that all of your moves for separating your variables are multiplication and division. Because addition will carry the d's with them and they'll get stuck, and you won't be able to separate them. Okay, so now we have something involving v and dv over here and something involving dt here. I can move the minus if I want, if it makes things easier for me. It doesn't really matter. But in order to integrate this, I'm going to have to write it like that. Unless you happen to know off the top of your head how to do that, which I never do. Okay, this will do. And now we can add integral signs at any moment once we've got the d's separated. So whack them in, and that's it. But so that the person reading this in the future knows what's happened, I am going to copy it. So all of these are the same relationship. They're describing how very small changes in velocity are related to very small changes in time. And then this is saying that if you add up a whole lot of very small changes in velocity, and add up a whole lot of very small changes in time, they should match up this way. Okay. Really hope this helps. And so what we do know is that there's two ways to approach this, and I would like to check which one your lecturer prefers. One way is to just do this as is with no limits on my integrals, with like a plus c somewhere. And the other one is to do it with limits on the integrals straight up. Which one does your lecturer prefer? She does it both ways? Of course she does. But in this one, I do have information about 2 times. And so I can put the time equals 0 and time equals 6 here. And I do have information about one velocity and not another one. And so I can do those things. So I can say this goes from time equals 0 to time equals 6. And the matching velocity at time 0 is 12. And the v is 12. And the matching velocity at time equals 6 is currently unknown. Now, most mathematicians feel uncomfortable with having v as both the variable and the name of a specific value of that variable, because this v is representing all of the velocities between here and here, whereas this v is representing the specific velocity at the end. If that makes you feel uncomfortable, you can put a symbol on this to tell you it's the one you're looking for. Some people would put like a v star to saying it's the v I want. The v in focus, or some people might put like v6 for the velocity when time is 6, whatever works for you. or VF for V final, whatever. I'm going to call it V star because that appeals to me today. Okay. Right, and so now I do both integrals completely separately. So on this side, B is a constant, it's the number 0.04. And when you integrate a constant, the variable attaches to it. If I was doing it with x's, it would be bx. But it's bt because the variable's t. And I am saying t equals to remind me what the variable is, because otherwise I would be the sort of person who would sub it into the b instead of the t. Okay. And just to check, if you differentiate this with respect to t, the t will disappear and you'll be left with a minus b. So, okay, and on this side, the integral of something with an exponent, you put the exponent up by 1 and you divide by the new exponent. And you do that from v equals 12 to v equals v star. Okay. I do note that both of these have a minus, so I can probably cancel that out now. Okay, so I've got v to the minus 1, which is 1 over v. So I've got v star to the minus 1 minus 12 to the minus 1 is b times 6 minus b times 0. Because you put in the top number and you put in the bottom number and you subtract. I have been extremely careful to explicitly say b times 0 because not all situations when you sub in 0 will the answer be 0. That's a trap that I fall into if I'm not careful. So I always explicitly write the bit where I put in the 0, even if the answer comes out to 0. Because there are times when it's like an e to the power of, and it won't come out to 0 when you sub 0 into it. So that's some advice for the future. And so I have 1 over v star minus 1 over 12 is 6b. And so now it's algebra. And so v star is this. Cool. Whatever that number is. So what was b? 0.04? Right. So that's like 1 over 0.2 something. 12th is about 8.8, 0.08. So it's going to be about 3. Right. So I'm thinking it's this one. But even before I calculate it, I'm going, oh, it's about 3. That's about the right one. But that's what calculators are for, people. So yeah, do the job, see what works out. And so, yay. Yeah. They've been quite sneaky in putting them all quite close together. I'm sure that at least a couple of those are designed specially to be the answer if you had made a mistake somewhere. I wouldn't be surprised if the 3.74 happened if you did a minus 12th instead of a plus 12th. No? Worth a try. Oh, that's even worse. Okay. Cool. Yeah. So, thoughts about this? Okay. All right. Okay, good. So that approach, yeah, let's see what happens with the next one, see what happens. So this is 2021 exam question 2. Particle experiences an acceleration of a is minus cx. Okay, so before I can even continue, damn it. Before I even continue, the acceleration is now a function of the position. Okay, And then they've done the C again. They've done the classic where they give it in variables. It seems to me that it's probably easier to just leave it as a letter all the way along and sub it in at the end. Okay, the particle has an initial velocity of 5 meters per second at x0 is 3.2. Which of the following values is closest to the displacement of the particle? So the goal is x. When it first comes to rest, when v is 0, at the first moment that v is 0. Okay. Ooh, interesting. Okay. I'm just thinking about the story here. When time is 0, not that time is part of this story at all, but it makes it easier for me to process this way. The velocity is 5. The acceleration would be minus c times 5. And the position, I guess, would be 0. Because x is the position you're up to. Oh, no, not times 5, times 0. Right. Is that right? Oh, it is 2. Good move, good move, good move. That's sad. It's so much easier if the original position is 3.2, but I guess if the original acceleration is 0, then it wouldn't stop. Change that, yeah. Okay, so it's accelerating quite quickly. Like, because that's like 2.29 times 3.2, we're looking at, 7-ish, 6 or 7 meters per second squared. It's currently going at 5 meters per second. It's only going to be like a second away from here or less before it stops, is what we're expecting. But I mean, and the acceleration is getting faster the further we go. Like it's accelerating faster the higher x is. So yeah, okay. It's going to be like under a second before it stops. Not that that's probably relevant, but I like to think about those things just in case. Okay, and then at t equals, we don't really care. And the velocity is 0 at this point. And then the acceleration at that point is whatever it is, we don't know. And the x is this, and this is the goal, to figure out what the x is at that point. Okay. All right. So it seems to me that what we need to do is somehow connect velocity and position. All right. So acceleration, we do know, is dv on dt. And we have to somehow get an x in there. You can get an x in there. This is not relevant, but I'm just putting it in here. That has an x in it, but it's got a t in it, and we don't really have any information about what time this is. So that's not helpful today. But I do have that. Can I just say here, there's something I want to say, but I don't want to impede the flow. So can you remind me later if I forget to say it? All right. Okay. So this is my favorite trick in dynamics. It's so cute. I'm just going to put an x in there. That's the trick. It is officially the chain rule, but it feels like at the moment when I'm doing it, straight up fraction cancellation. Like, oh, look, that cancels with that. Derivatives behave as if they were fractions most of the time, which is why it took us so long, like 100 years, to really sort out all the details mathematically of what the hell they were doing. Yeah, but Newton just blithely wrote this stuff. Okay, so that's got an x in it. We're just going to plonk one in there, and dx on dt is also v. So some people are capable of remembering this directly. I am not. I have to go through this path to get there. Okay. Which is great because this has a v and an x in it, and that's the information that I need to connect together. So I have that a is minus cx, so dv on dx times v is minus cx. And so if I put the dx up there, I will have minus cx dx and v dv, like that. Okay, and we have position 3.2 up to position we don't know what that is. And we have velocity 5 up to velocity 0. Or down to velocity 0, I guess, but it's up in the purposes of the integral sign. So these two events of x being 3.2 and v being 5 go together, and these two events go together. How are we feeling? And so, um, we'll do this one. And so exponent will go up by 1, and I'll divide by the new exponent. And I'll go from v equals 5 to v equals 0. And this one, same deal. The minus c is multiplied on, so it will still be there. And the x will go up to x squared, and I'll divide by the new exponent. And so I'll get x equals 3.2, and x is whatever x is at that moment. Okay, so the top one here is 0, so I'll have a half of 0 squared minus half of 5 squared. And the top one here is x star. And then the bottom one here is 3.2. Damn it, I've lost my half. That's a double minus there, which I could write as a plus, but I just want to write it as a double minus to make sure I've done everything properly. Okay. I'm only slightly uncomfortable with doing it this way because the way that this moves might cause there to be more than one place where x will work, but I guess there'll be two solutions because I've got an x squared, so that's okay. So we've got minus 12.5 is minus c on 2 times x star squared plus c times 1.6. Oh no, 3.2 squared. Oh gosh, that's what calculators are for. No, not going to do that one in my head. What? Sorry, that's the 3.2 squared. Is that right? And so I've got, I'm just going to put this over here and this over here. My c on 2x star squared is 12.5 plus c times 5.12. Oh, that's funny. Oh, they've all got halves in them. I could have cancelled that out all the way back there. All right, that's better. All right, makes me feel so much better. It's halves everywhere. And so I've got c lots of x star squared is 5 squared plus c times 3.2 squared. And so x star squared is 5 squared on c plus 3.2 squared. And so x star is plus or minus the square root of that. There's a double minus here, which became a plus. And I moved this over here and this over here, so that stayed the way it was. Rather than reversing the whole thing and minusing stuff, I felt that would be make my minuses safer. Okay, and someone needs to tell me what that is. I do have a calculator here. I should probably just go and do it myself. 4.6. That's earlier. Huh. That's no, it started at 3.2, didn't it? It was the speed was 5. Okay. That's okay. Yeah, the C is no, we know what C is 2.29. But X naught was 3.2. And so it has moved forward. Good, it's supposed to move forward. It was going at 5 meters per second to begin with. And it shouldn't move backwards, so that we don't really want the minus because it moved forward to begin with. And it would have to turn, would have to stop and turn if it went backwards. So it definitely cannot be the negative answer. So we're just gonna not minus. Okay, cool. So X star is like 4.6 meters. Yay. Okay. Awesome. I'm feeling I can do this. Do you want to do one more of these? And then we'll have a chat about that last question and just go all in. Okay. I did, yes. And I think thank you so much. That's why I tell people these things. Back here when it was a second derivative, that's when you need to do it with the plus C's and stuff. Because it gets confusing to do a definite integral and then another one again later. Like you can't deal with a second derivative this way. You have to do it the other way. So I suddenly had a thought at this point as to why you would do the other one. And so if you get told acceleration as a function of time and you need to know positions, then that's when you should do it with the plus C's. Yeah, that's my guess. Could be wrong, but have a look at the way your lecturer's done examples and see if that works. And actually, this is a useful piece of advice. Might be too late for you guys, but for those watching this in the future, one of the things that we're not good at as university lecturers or students is figuring out what it is about the question, telling you what it is about the question that told me what I should do in response. But you can figure that out. If you want to know what it is about the question that tells you how you should respond mathematically or with physics, then you should take note of how the lecturer responded and what the features of the original question were. And especially you should take two questions that had different responses and figure out what was different about the original situation and what was the same. Because anything that's the same, if the response is different, but the original questions are the same in some aspect, then that aspect doesn't tell you how to respond. So anyway, just wanted to point that out as a thought about how to go about making sense of some of these things. Also, you can just explicitly ask the lecturer how they decided, but sometimes they don't know. A lot of people who have done things for a long time don't know how they do it. Much as if you have to explain how you tie your shoes, you often realize you don't know how you do it anymore. Yeah. Yeah, your brain just holds all of that in tying my shoes. It doesn't have the individual bits in below anymore. Okay, I'll do one more. Or maybe we'll see. A particle travels along a curved path defined by the equation y is b times ln x, where b is 0.2. Okay. Oh, did we get an answer that was on the list?
Yes.
Oh, because they asked us what the change was. So I really should have checked that we had an answer that's on the list. So the change in X is the 4.6 minus 3.2, which is 1.4. Yes? To C. Okay. It is, in fact, one of the options. That's a good start. Wow, that's an important message. Go and, if it was a written question, it's a really important message to go back and find what the actual question was and not just stop without getting to the thing that they actually asked for. Nice and multiple choice question. You can go and say, what? That's none of the things. Oh, I see. Okay, particle travel along a curved path described by the equation y is b ln x. Well, ln x looks something like that. So don't know if that's helpful, but it helps me. And 0.2 ln x will just be even flatter, so that'll do. And I know ln x looks like that because e to the x looks like that, and so it's the inverse. All right. And okay, when x is 4 meters, at this point here. All right. So when x is 4 meters, the velocity in the x direction is 5.2 meters per second, and the acceleration in the x direction is minus 2.2. Which is the following is the closest to the y component of acceleration? So y we could figure out, that would be, 0.2 times ln of 4. And ln of 4 is just a little bit more than 1. So we've still got a y coordinate being quite small, like it's under half. I mean, that's what calculators are for, but, Vy we don't know, and Ay we don't know, and this is the goal here. Okay. So it is moving this way, right? And if it's moving that way, it's going to have to be moving up in order to follow this curve. And so it's definitely true that Vy is going to be positive. And if it's slowing down in this direction, it has to be slowing down in the other direction as well, I reckon. So I'm reckoning that my Ay should be negative, is my guess. But again, my instincts are often wrong with physics. So that's my, all right. All right. Cool. So this feels to me, nope. Take a moment. Calm down. Right. As it says on the Maths Learning Center wall, the first step of problem solving is to prepare yourself. So prepare myself. What I know about dynamics at the beginning is that there are two things that are in tension all the way through dynamics. And I've said this to a couple of you before, that there are things that if you know about how it's like accelerating and its velocity, then you can figure out the way that it's moving, like the path it's moving on. And vice versa, if you know the path it's moving on, you can figure out the way, like the speeds and the accelerations it's moving at. And that is the story we're in here. We've been told the path, and we have to be able to figure out these things. But we only know what's going on at this path at this exact moment. So it seems to me that because we're only thinking about this exact single moment, and we're talking about the way it's moving on this path, we really only care about what's happening at this exact spot in the path. And so if I zoom right in on this spot, my magnifying glass there, it's going to feel flat. not flat, but straight. That's the whole point of derivatives. And so there'll be a velocity with x and a velocity with y, and they together will have the same slope that the curve has at this point. So if I was asked what the velocity of y was, I would actually be able to figure it out from the slope of this curve, which is the derivative. They didn't ask me that, but it would do it. So this slope is dy and dx. And so using that slope, I could in fact figure out what Vy was. They didn't ask, but it's possible. Okay. And so here's my next piece of probably magical thinking, but if the first derivative with respect to dy dx tells me what the velocities are doing, it seems reasonable that the second derivative should tell me what the accelerations are doing. And now I'm going to go look at the formula sheet, because that seems like a useful piece of information. And where the hell did I put it? Right. This is interesting. I've got a second derivative with respect to x here. Okay, that's telling me a radius of curvature. Oh, yeah. I guess if the slope of the line tells me how I'm speeding, then the curviness of the line should tell me how I'm accelerating. Yeah. Well, anyway, makes sense when I say it aloud, but as it'll do. Okay. And where is the radius of curvature in the rest of, there it is. Tangential and normal coordinates. Sweet. And what do they actually want? AY. Nice. Bear with me just a second. So AY would be dy and dx, right? dy and dt. No, sorry, dvy on, damn it. That. Just bear with me. I'm just thinking about this. This is probably not the most efficient approach, but I just want to think it through. Yeah, that's not helpful at all. But let's not go there. Yep. Yeah, you're going to get me to do it in one coordinates and then rotate back to the other one. Sweet. Yes. Well, just a second. I choose to look forward to this. I prepare saying, yes, we can do it. Okay, but that slope is going to also help me to figure out the relationship between the tangential normal coordinates and the XY coordinates as well. Okay. I can deal with this. We can deal with this. Okay. So this is not one of the questions like the previous two. It's not about integrating and stuff. It's about other things. Okay. Right. So just to track through the way this formula sheet was working, we discovered that this was a thing we could figure out from the equation of our curve. And then that was in here, which is in tangential normal. And then somehow we have to transfer that into x and y. Right? Okay. Well, let's just do the bit that we're sure of how to do at this time. So the radius of curvature, I'm not going to say equals, I'm just going to say it's my heading. So y dash is b times 1 over x, because y is b ln x. So the derivative of ln is 1 over The derivative of ln of a number is 0, but the derivative of ln of a variable is 1 over the variable. And then y, and that is b times x to the negative 1. And so y double dashed is minus b times x to the negative 2. Cool. All right. And what was b again? 0.2. And so we need the absolute value of y double dashed would be b on x squared, because the minus will go away. And that is 0.2 on 4 squared, which is a terribly small number. I'm just going to call it b on 16 at this time. Okay. And then 1 plus y dashed squared is 1 plus b squared on x squared. And we need that to the power of 3 on 2. Sweet. And so rho is 1 plus b squared on 4 squared to the power of 3 on 2 on b on 16. Okay. Probably I could have just skipped a lot of my figuring out, but, you know, 4 squared being 16 seems such a natural thing to write. And that will come out to an answer of some sort. Should get my own calculator, really. One plus 0.2 divided by 16. No, 0.2, that's a square, to be squared, sorry. Power of 3 on 2. And then all of that is divided by 0.2. Also, yeah. I get 80.3. Okay. And so that's telling me that the acceleration in the normal direction is v squared on, so annoyed. Yeah, but that's not Vy. That's, I'm going to have to figure out what Vy is to know what V is.
Oh, sorry. Yeah, I did that.
Yeah.
Yeah, I did that as well.
So I had to do this all along. This exact thing that I was doing here, I had to do all along. Okay, cool bananas. We'll just do that anyway. And so we've got Vx and this is Vy, and Vx was 5.2. And this slope was y dashed, which was b on 4, which is 0.005. No, 0.05. And so we have that this must be 0.05 times 5.2. Oh, yay. Oh, that's so cool. Sorry. You know, this quantity just here is the velocity times x, Vx. Like Vx times that is the velocity. Yay. Yeah. So this is just cool. 1 plus y dash squared square rooted is times Vx is what Vy is. Yeah. Yay. Cool. Because this is going to be y dash times Vx. And so when you find this length, you're going to square the Vx and square the y dash times Vx. And then you'll factorize out the Vx and so cool. Anyway, and so the Vy is therefore the slope times the Vx, which was whatever it is. What did you say that was? And so therefore V is this, which is not much different from 5.2.
I think what we're looking for is where I think
Oh yeah, we don't care what V squared. Yep. Because the formula has a V squared in it. Okay, cool. Okay, so let me just pause for a second. Just need to take stock of what happened there. When I zoom into this, the two speeds at which it's moving will be the slope of the line. The slope of the line is y dashed. And the way that slopes work is the x change times the slope is the y change. And so that's what I've done there. And then the actual velocity is this velocity here, which I got from Pythagoras' theorem. But as you've said, the formula for an has v squared, so I don't really need to square root it. Okay, and so now my an is 27.1076 divided by rho, which was 80.3002, which is going to be about 9, a ninth, so about 0.1. Sorry? Oh, yeah, that makes more sense. Sorry, I'm making up crap. I got in my head the 3's and the 9's mixed up, because that's 3 cubed and that's 9 squared, and I thought it was 9, that was 9 cubed. Anyway. So you're saying it's about a third, right? 0.33. Okay, so that is the acceleration in the normal direction. And I actually am going to need to know the acceleration in the tangential direction to figure out the acceleration in the y direction. So I need to know what v dot is. Well, the formula sheet says that the acceleration in the tangential direction is v dot, which is the speed, the time derivative of speed. Yep. Oh, so you think we can figure it out? Okay. Okay. But how do we know how long it is? No, that's how long the normal one is. Oh, okay, maybe. Okay, I think I get what you're saying. Is it? So there might be a different approach.
Yeah. Dylan mentioned it. Yeah.
So let's just step back a bit. I should have just run with this. Should have just run with this. But that's okay. We talked about a lot of cool stuff. And I have to say, that was fun. If someone wanted the radius of curvature, we know how to do it from the information we've got, and we know how to figure out the normal acceleration from that. But perhaps you're saying that we can avoid talking about normal at all because it is in terms of y and x already, and we know how y is a function of x. So let's just go for it. So y is b times ln of x, which means that the derivative of y with respect to time would be b, because that's a constant multiplied on, times the derivative of this with respect to x times the derivative of x with respect to time. There's the chain rule with that. So I differentiate this with respect to the thing, but the x is also a function of time. So I have to imagine that that needs a derivative too. So if I just want to write this explicitly, dy on dt is b times 1 on x times dx on dt, because x is a function of time.
I will.
I'm so happy because this is exactly what someone asked about. So if I differentiate again, now there's two things that both have time in them, because this dot here is a derivative with respect to time. So this is a d on dt. I need to look out for functions of time. So x changes with time, and so it's a function of time, and that changes with time. So I'm just going to rewrite this as bx to the minus 1 x dot. So two pieces. The derivative of that with respect to time is b times minus 1 x to the minus 2 times x dot. And then I keep this x dot. And then I keep the bx to the minus 1 and differentiate that with respect to time. So I've got that. Yes. So minus b x dot squared on x squared plus b x double dot on x. And we know all of those things. So x was 4 and x double dot, so x single dot was the velocity with respect to x, which was 5.2. And x double dot was the acceleration with respect to x, which is minus 2.2. And I can put them all in and it tells me what y double dot is. Yay, that's what you were doing. That's much simpler.
I think more tricky assignments. There are often many ways to answer the questions, but there's some that are a lot faster.
So what we need to figure out now is how to have thought of that before getting stuck in the other one. But we'll get there. I just want to finish it for my own completeness' sake. So the Vy is this. They wanted the Ay, right? That's what the goal was? All right. Ay is this. So that's minus 0.2 times 5.2 squared on 4 squared plus 0.2 times minus 2.2 on 4. Okay, so definitely a negative number. Oh, they're all negative. That doesn't narrow anything down.
Have done these.
448. Okay. Is that one of the answers? Yes. Yay. It's also C. I think they've all been C so far. Okay, so I guess I really should have taken my earlier advice and gone, I need to somehow connect the acceleration at y to what's happening at x. And so I should use the relationship between y and x. But I got distracted by the formula sheet. So I think that's a relation between y and x. And I need to keep in my mind that x and y are already functions of time, or I wouldn't be able to write x dot. So I think the person writing this exam was strongly hinting by calling it x dot that I should differentiate with respect to time. Yeah, okay. So take their hints, is the message. Right. So the thing that told me at this point that I was going to get into problems is that I needed to know what v dot was, which means I need to differentiate the speed with respect to time. Like this is the true acceleration, not just the other components of acceleration. And how do I figure out the true acceleration if I don't know the y acceleration? Because that's what the goal was. So Yep, okay. And that does tell me a little more about how this works, is that if I'm going to use this tangential normal thing, I'm going to use this, then actually the v dot can only be figured out from your x, y. Really. The v dot is the true acceleration. Well, yeah. Yeah, v dot is the rate of change of the magnitude of acceleration. Right. Right. Well, I've learned something. Thank you, Gareth Bridges, who wrote that exam in 2021. Okay. Well, we're going to just go gung-ho and try the last one? Or do we want to do something less ambitious? All right. Well, it's good to approach things that scare you, so let's do it. What's that? Let's do it then. Well, let's think about it. We have about half an hour, and we will think about it to that extent. So I do not know if your lecturer writes exams in the same way that Gareth used to, but it does appear that the questions in the 2021 exam were in course order. The thing with rolling is the last question, which is also the last thing you did in dynamics. So I don't know if your current lecturer thinks about exams in the same way, but that's something that I noticed. Feels like it, but I don't know yet. A solid spherical ball undergoes a pure roll, meaning it doesn't slide. Is that what it means? Meaning that the surface of the ball is in contact with the surface it's rolling down at any moment. And the distances it goes here is also the distances that the ball goes. That's what a pure roll is. Okay, good. Just making sure I know what that means. Down a circularly shaped slope. Okay, it's a circle. That's good. From rest at the apex, as shown in figure 9. The apparatus is in the vertical plane. Okay. I'm going to copy this picture. That seems like an appropriate thing to do. So that's what it looks like at time number 1. And they're saying that the radius of the ball is R2 and the radius of the circle it's rolling down is R1. And then this is time number 1. And over here at time number 2, which is not necessarily at 2 seconds, now it's here. And it's rolled along this a distance of theta. And they're telling me that it's doing that because of gravity. Okay. Though unless you knocked it, it would balance you could probably, if you were very careful, balance a ball on the top of another ball and it wouldn't roll. But that's not how, if they were both heavy enough. Sorry? I haven't written them down yet. So R1 is 4 meters. R2 is 0.02 meters. So it's like a ball bearing as opposed to a tennis ball. And the mass is 10 kilo. Wow. Oh, no, that's 2 centimeters, right? Yeah, yeah. That's a heavy, that is a dense ball. That is that is 2 centimeters in radius and 10 kilograms. That is a very dense ball. Wow. Oh, I love it. I probably shouldn't have stopped to think about that, but it's that would distract me in an exam, I have to say. Okay. So before I look at the question, the first thing that occurs to me is I can figure out, they haven't told me what theta was, have they? Okay, but I could theoretically figure out that I do know that this distance along here is R1 times theta if theta's in radians. And that means that the part of the ball that kind of wraps along here is that same distance. And so by the time it gets to here, that's wrapped back this way. Yep. Okay, just thinking it through. So that this point here ends up at that point there. Just making sure I've got that going. Okay. So part A says, using the work energy principle, or otherwise, yeah, they don't usually mean or otherwise, but shows that the speed of the ball as a function of theta will be approximately that formula. Hint, R1 is a lot bigger than R2, so you may ignore the effect of the size of the ball on gravitational work. So they're saying when we think about the distance that it has traveled vertically, just do this distance. I think that's what they're trying to tell us. Okay. So the work energy principle says what? That's what we need an answer to. And it's your job. Subscript.
One, one.
And is that on here somewhere?
Uh,
Oh yeah, okay, so it's there. And the work of the forces is basically the force times the distance it moves. The force causes the thing to move in the direction the force is facing, which is what the cos theta is about. That's the cos phi. That's the angle between the direction you're moving and the force at the moment. This, in case you're wondering, this notation, just while we're at it, I'm just going to write this down. I'm really just for a second. This notation they've been a bit free and easy about where to put the ds. It can go anywhere. This ds stands for a very small change in displacement in the current direction that it's currently going. And this s stands for the path. small piece of path. Yes, this is a multivariable calculus concept, like notation. So, but yes, having a single thing at the bottom there means the name of the object across which you are doing the integral. So just in case you were wondering, so theoretically, you could do like, the integral from 1 to 2 of f of x dx. You could write that if you wanted to as the integral along the path from the number 1 to the number 2 of f of x dx if you wanted. But most people feel uncomfortable about this, but that's what this notation's about, in case you're wondering. But if you ever do a course called multivariable calculus or vector calculus and electrodynamics, this notation will appear. But it is a common common thing for physics lecturers to do, to write down math notation that their students have never seen. So, yeah. But in general, what this means is that if it is traveling in a straight line, then if it's traveling in a straight line, then what you need, traveling in a straight line in the direction the force is currently going, it will be force times distance, right? So it would be force times the distance in the direction of the force, or the force in the direction of the path times the length of the path, either way. Force in direction of travel times distance. Either one of those will work, pretty much. Okay. So in your case, because the only force acting here is well, technically there's a normal force, but that's a normal force can't do work, okay? Because that's stopping you from going inside the thing. And so relative to the normal force, you're not moving in that direction. Okay, thank you so much. That makes so much more sense now. So I just want to repeat, so saying that the normal force is always pushing outwards and it's never moving inwards. And so the normal force doesn't do any work. Oh. It's perpendicular to the speed. Cool. So because both because of the mass, which is perpendicular to it's always perpendicular to the direction of travel. And so there's yep. But also just from logic, it doesn't move into the surface. And so the normal force, which is what is keeping it from moving into the surface, isn't doing anything. Okay. I mean, it is, but it's not moving it. Yes. Okay. I'm so excited. That's great. Thank you. Learn something. Let's hope I can remember it in like 8 months' time. So the force of gravity, which is mg, times the distance that it moves, which is this distance here. We shall call this h. H. So this is the u12, right? That's what we're saying. Mg times the change in y. Okay. Well, let's call it that. Okay, so just a second. I'm just going to draw this picture again. So the first distance is R1. Yep. And then this distance, damn it. The first height is R1. And then this distance here would be R1 cos theta, because it's next to the theta in this right angle triangle. And so therefore the change in y is R1 minus R1 cos theta, which is R1 times 1 minus cos theta. Is that what we were aiming? Where's the question gone?
No, it's always.
Sorry? Okay, that's all right. No, just
It does. reflect.
Yep, I'll get there, but yes, but there was 1 minus cos theta in the formula, wasn't there? I've just lost the question, so I can't. Here we go. No, not that. Here it is. Throw everything else away and try and. So there is a 1 minus cos theta in the formula we're aiming for, so that's a good move, good sign. Okay, and then so we've got that the U1 to 2 is mg times R1 times 1 minus cos theta. And then the kinetic energy, what did they want? The speed. So we do know that that's equal to the kinetic energy, and kinetic energy is a half of mv squared. Is that right?
Like, explain the question, they asked about their rotation. I omega squared, which is wait.
Oh, because it's rotating too. So there's some other crap going on.
What's the question?
Ah.
Oh, great.
I think it is because this that should be on page 3, right? Where is that? This thing here, right? And then I for a sphere is mr squared, but r is 0.02 and 0.02 squared is really small. So I think that's saying that we can ignore that. Just to be clear, this is 2/5 of mr squared, and that is small. And so we can get rid of that. I reckon that might be what that comment is about. Yeah, this is the velocity of the center of mass. Yep. And is that what they asked us to find? They just said the speed of the ball, which I presume means the speed of its center of mass. That's okay. But we have talked about a lot of the concepts, and that's the important thing about the seminar. That's what it's for. Ah, okay. So just, but wait. Just to be clear, this should be T2 take T1, right? And T1 will be half of mv squared, which is plus half of I omega squared. But these are both 0 at the beginning because it goes from rest. And so, yeah, so T1 is 0. And then T2 will be half of mv squared plus half of I omega squared. And then we do know that this is 2/5 of mr1 squared, which is small. And so we cross that out and we get that in the end. And this minus 0 is, okay. So therefore the change in t, right? Is just half of mv squared, approximately. That's what we're saying? No, because I think it's just that potential energy isn't part of the work principle? Like, yes, I think I could be wrong. People may correct me, but I think that the potential converting to kinetic. I think the U is the change in potential energy. Ah, if, yeah, that's the change in potential energy. So yeah, you're right. This is the potential energy that it has here that it doesn't have here. So it seems to me that that work energy principle is the same as the potential versus kinetic energy thing. Who's saying that the work is the loss in potential energy. Energy is conserved. Yeah. So this work is the potential energy that went away and became kinetic energy. Yeah. And so it all works out in the end and it works fine. Okay. That is cool. All right. We have dealt with our technical details so that we are all feeling good about what's happening. And so what we're saying is that this is if the radius was 10 instead of 0.02, well, I mean, maybe not 10, but if the radius was 1 meter, we would have to consider this thing. Yeah, because we'd be multiplying by 1 squared and there'd still be stuff here. But because we're multiplying by 0.02 times 0.02, which is 0.004, it's small. Okay, sweet. And so what we have is that mgr1 1 minus cos theta is the same as a half of mv squared. And so the v's cancel. And I've got the v squared is 2g1 minus cos r1 1 minus cos theta. And so v is the square root of all of that, right? And then the shape that they've given me to compare to has a single number out the front of thing to the power of a half. So I should separate this root into the root of the numbers and the root of the formulas. And power of a half is what roots are. And so that 7.48 ought to be the square root of 2gr1. That's a good question. I think it's 4. Do they use 9.81 or 9.8? Oh, that's distressing. What did we do wrong? Yep, maybe. Maybe we put that back. Why not? Let's see what happens if we put it back. The Amiga's it's freaking me out though there. Yeah, this is like root 80-ish, and so it's going to be like 9-ish. Yeah, okay. Well, maybe we should. We were wrong about that. Or maybe we weren't. Wouldn't that just make it bigger?
No, it's not too big for one.
Oh, because you got to take that off. Gotcha. Yep. Okay. Gotcha. Okay. So the hint was just to figure out this delta y. Okay. Okay. So I is 2/5 of m r2 squared, I guess. Is that how it was? Yeah. So that's 0.2 times 10 times 0.02. Is that right? The radius of the ball. The radius of the ball was 0.02, yeah. It so is 1/5 is 0.2. Trying to be clever, but that's okay. So we have 4 times whatever 0.02 squared is. 0.02 squared would be 0.0004. So 0.016. 0.0016. 1, 2, 3. Yep. Cool. Okay. And then we have to times that by half and times omega squared. And you're saying that the rotational speed will be based on this reasoning here. Okay. So how do we do that?
R1, the theta,
Mm-hmm.
R2, omega.
Okay. So are you saying you're saying that the speed at which velocity are you talking?
R1
Yeah.
is velocity, like the velocity going across, like the velocity going that way.
Yeah, around the circle.
And it also the velocity. Yeah.
Okay, so we're saying that this and this that we're talking about there. So this is the piece of big circle we've unwrapped, but we've unwrapped that off the little circle, and this is R1 theta, and this is also R1 theta, but it's also R2 times, yep, so R1 theta dot times omega. Okay. But it is not on the formula sheet. Cool. So what's that? That's for a rolling object on a flat surface. Okay. And so theta dot is R2 omega. No, what did we want? Omega.
Oh, wait.
So this is where we're getting into stuff that I haven't done in a course of my own. And so this is now a past session. I'm just here to help you talk to each other. So how are we dealing with this? Oh, okay, because this is V. Right. That means we're solving a quadratic equation. What the fuck? Oh, that's okay, because that's all right, because the v will get squared and we can wrap it into the other bit. Yes, okay. So v over R2. Yeah. So that's what I was trying to do. So this is the distance it goes is kind of R theta. And then the rate at which that changes is R theta dot. Like, and then, yeah, so the like the literal distance it goes is R theta, which means the literal distance this goes is also R theta, the big R theta. When you're doing it rectangularly, it's the same, like the distance it goes is just straight, X. And then this is like X. And so the distance it's moving, like I'm just going to say that this is a distance. This distance is this distance, but then the speed at which that distance changes will be R2 omega, because that's how it works in the small circle. And the speed at which the distance is changing is the current velocity. Yeah.
That's the biggest sort of one extra.
Yeah. Yes, because when you're dividing by 0.02, that becomes a very large number. And so once we've got that, so now we've got that. What page was this? So now we've got yeah, the change in height of the ball. No. Yeah.
That's what that's what we're saying.
So I'm just going to repeat that. The change in height of the center of mass of this ball is not, in fact, this height. It's this height and a little tiny bit because it's been rotated. So there's like a cosine sign of the amount that the ball's rotated. But because the ball's so small, that extra bit of distance isn't going to make a difference. And that's why they said what they said. Okay. Okay, so we're here, we've got this thing, and we know what that is. That's the mg R1 1 minus cos theta, that's this bit. And this bit is a half times 0.0016 times the velocity on R2 squared. And that's a half of mv squared, and they've both got a v squared. And so I can pull that out. Yeah. Oh, that 0.0016. Oh, for the sake of fuck. Sorry. I didn't need to know what this was. I could have just used it there. Oh, that's just glorious. Look at that. That's amazing. And the R2 squareds cancel. And so does Matt. Well, but on the other side, yeah. Oh. So we end up with the half of the m and the v squared is in both of them. And they cancel. So we've got 2/5 plus 1.
It's R squared on top, R on one. So
Yeah, but that's inside the square.
okay.
And so the half mv squared is in both parts, and we're left with a 2/5 plus 1, which is 1.4. And a half times 1.4 is 0.7. Oh, just look at them being nice, but we didn't know they were nice until we got to the point where we solved the problem. So that just tells me again, it was against my better instinct to figure out what this was, because all the other questions they gave us letters, and it was easier to keep the letters. So that's a new strategy. And this is now, what was it? 2G, no, MGR1, 1 minus cos theta. And so the V squared, the M's cancel, and we're now dividing by 0.7 here. I'm really hoping that that is coming out to the right answer now. And that is the 7 point whatever it's supposed to be. I will upload the pages. Ah. Well, we did the first question, which was worth twice as much as the second question. I will also upload the questions that go with them as well. So show that the normal force acting on the ball when theta is 25 degrees is approximately 75.7 newtons. Tell me about that question.
They're in the normal direction. Forward to
So just to wait. Can I just draw a free body diagram? So we've got on this ball that and that and probably friction, but I guess that's not really doing anything in the context of this story. It's keeping it rolling.
yeah, and then we know squared off word.
Ah, okay. Wait. So just bear with me. Okay. So the acceleration in the normal direction is v squared on rho, according to previously learned stuff. And because it is in fact traveling on a circle, the rho would be what, radius 1 plus radius 2? Radius is there. Okay. Cool. I mean, the 0.02 is not going to make much of a difference to the okay. And then so the acceleration in the normal direction will come from the force. And the force in the normal direction, I'm going to have to cut this into its normally directed bit. Yep. And so this thing will have a piece in the normal direction and a piece in the tangential direction. And the tangential direction piece is what's making it roll down the hill. Okay. I'm feeling better about this. And so this 25 degrees, if we go parallel wise, well, that'll be 25 degrees up there. And so therefore we have that the mg that's 25 degrees there. And so the normal piece of this will be mg cos 25 degrees. Because I don't know, what's the question? So I think we're finding the normal acceleration so that we can find the normal force. Yep, so the total force in the normal direction is the normal force from the surface and the gravity pushing into the surface. So total force in normal direction is n outwards and mg cos theta. Is outwards the traditional direction? Not that it matters because we're just going to do the magnitude, but is that. And Yeah. And so we have that minus n plus mg cos theta is m times the normal acceleration. And the normal acceleration is v squared on rho. And we just figured out v. And so n is therefore, put that over there, mg cos theta minus man, which is mg cos theta minus mv squared on rho. Yes, okay. And we just found a formula for v based on theta, so we can sub that in. So v is that 7.481 minus cos 25 degrees to the half. And rho is radius number 1, so we can sub that in. The m is 10, and the g is 9.8. And that's 25 degrees as well. When we sub that all in, it gives me what n is. Okay. All right. Thank you. Oh, well, I hope it was useful. And yes, I'll let you know where the notes are when they end up somewhere. I will stop the recording.